Hi there, it's Mr. Poe from Winton Grammar School for Boys, and this is going to be Algebra and Number Theory Session 8, and we're going to be looking at polar coordinates. So before I begin, a bit of rationale why I've put it in the Algebra and Number Theory section. Well, when I initially wanted to start these videos, I wanted it to have a mixture of different topics from different branches of mathematics. And the reason why I chose those branches, mainly algebra and number theory, geometry and vectors, calculus, mechanics, probability and statistics, decision or operational research techniques really, and recreational and competitive mathematics, is mainly because, well, for one, I wanted to break it up and do lots of different things so it would keep the momentum for me going, so I could do stuff every day and I'd be like, oh, what are we doing today? That's interesting, it's new. Two, I wanted it to have some kind of natural follow-on structure, and also so that really the first 3 days, i.e. of the week, which is algebra, number theory, geometry and calculus, geometry and vectors and calculus, are mainly what I would consider pure mathematics, whereas the latter 3 days, mechanics, probability and statistics and decision, would be more for the applied, and the recreational competitive maths would just be a little bit of fun on a Sunday, doing some interesting problem solving, but I guess that would just be applied, it would be core or pure mathematics, but more in-depth problem solving, I suppose. So when I thought, polar coordinates, I mean, technically that borrows from a lot of different strands of mathematics, I guess. If I was to look at the my mapping of what I've put it on, then I'd probably put it into the geometric part, i.e. geometry and vectors. But there's a lot of calculus techniques used when solving problems with polar coordinates, especially when we're looking at equations of tangents, areas bounded by curves, that kind of thing. And so really it was almost an arbitrary choice to put it in the algebra and number theory block. I think the only reason I did is so that, I can kind of cram it all in there, and you'd probably argue it's more of a geometry and vectors thing, to do with coordinate plane stuff, but essentially it's its own coordinate system. So yeah, it's an arbitrary choice. I would say though, algebraically, I think the link is that to be able to transform and deal with polar coordinates, i.e. going from normal Cartesian planes to polar coordinates, you've got to have your trigonometric identities pretty nailed down to see exactly what's going on. Okay, so let's enough of the chat. Let's just get on with it. So let's consider the Cartesian coordinate system. And so what does that look like? Let's recall the Cartesian coordinate system. So I've got an xy plane, like so. And I don't know, for a particular point, let's call this x naught, y naught. That's some particular value of x and y. Okay, now for polar coordinates, the way we would write this is this point would actually be written as r, comma, theta, where r is the length from the origin to the point, so this would be r, and the angle it makes with the x-axis would be theta. And in many questions we don't actually write x, we'd actually, in polar coordinates, we'd call it the initial line. Okay, so say for example, I had the point, let's suppose, e.g., I had the point 1, 1. So what does that look like? It looks like this. That is a terrible line, sorry. Like this. This is the xy plane. There's my point 1, 1. So pretty obvious, I'm hoping, that just from Pythagoras, if this is of length 1, this is of length 1, and that's of an angle theta, then the radius is clearly root 2, And the angle it makes, now we're always going to be using radians from now on, right? You need to get this idea of degrees out of your head. We're using radians, so if pi over 2 is a right angle, then this would be pi over 4. And that's pretty obvious to see where that comes from, because just inverse tan of the opposite, which is going to be the y coordinate over the x coordinate, is going to give the theta value. Okay, yeah, that's pretty much it for being able to identify points from a Cartesian coordinate system to a polar coordinate system. And just for the record, there is quite a few coordinate systems you could use. I'm hoping we can talk about them at some point. Just off the top of my head, there's spherical polar coordinates. There's quite a few. To be honest, I'll have to go away and research some of them because I haven't seen them in a few years, just because I don't deal with that kind of work. But I'm guessing some people use them all the time in their specific fields, and it's worth it. So, fine. Let's suppose I'm dealing with a problem. Okay, and the problem is this. Let's suppose that I'm dealing with a circle looking like this. And let's say the radius is 5. So it's looking like this. And now, let's suppose that I want to find the area within inside this circle, but actually I'm only interested in the area of this little sector here. So just for example, this point here would be 3, 4, and let's say this point on the circle is 4, 3. Okay, suppose I'm interested in this shaded region R. I'm interested in that region R. Okay, well, how would I go about doing this? Well, you could consider x squared plus y squared equals to 25, and then making y the subject, so then y equals 25 minus x squared, and take the positive square root, and then by doing so, by taking the positive square root, you would only be considering where the circle is, where the circle is above the x-axis, so looking like this. And then you could just integrate, but then you'd have to be a little bit careful, because then if you integrate, well, let's see what the problem is. If you integrate between 3 and 4, you'd find this area. So you'd have to subtract this bit. And if you integrated between 0 and 3, you'd have to subtract this bit and this bit. So actually, it gets messy quite quickly. And this is because when you integrate using the standard y integral of y dx, what you're doing from first principles is you're summing up lots of rectangles that are below the line. So I'm summing up this rectangle and this rectangle and this rectangle for some infinitesimally small dx wide, and when that dx tends to 0, it becomes the area. The problem is that's probably not a good way of doing it. So what polar coordinates does is it uses the fact that we're dealing with a rotation, right? We're rotating some theta degrees from an initial line, from some x, and we've got some r. So integration from polar coordinates point of view is, say I've got a curve like this, and I'm interested in the area from 0 to there, and from 0 to here. And let's say that this angle is theta 1, and this angle is theta 2. Then what we do, what's actually happening, is we're taking, if we zoom in, imagine that this infinitesimally small strip with angle d theta and both of these radiuses are the same, we're essentially splitting this down into infinitely skinny, if you like, sectors of angle d theta, and then when d theta tends to 0, that shouldn't be a curly d because it's not a partial derivative, when d theta tends to 0, then in the limit when d theta tends to 0, then you've actually got the area of that infinitesimal slice, and then we want to sum them all up. So remember, the area of a sector, I think we've covered before. Let me just see, when did we cover that? Radians and their applications to circles. Yeah, we did that 28th of April, quite a few days ago. So I would have done that in geometry and vectors number 3. Then the area of a sector would be half r squared, but now instead of theta it's d theta, and now I want to integrate all of that. And now if I want to find the area of this whole section here, then I just need to integrate between the large angle. They're like upper and lower bounds. So notice how if it ends, because it ends in d theta, these upper and lower bounds must be in terms of theta, or rather they must be angles. So this is when theta equals theta 1, and this is when theta equals theta 2. So there's an analogy here. Essentially, if you want to integrate in polar coordinates, just remember you're dealing with sectors. So if I was to go over to here, right, let's think about how I would do this. Well, in general, if I look back over to here, what have I got? Well, if I drop a perpendicular down, do you agree that this y is the same as r sine of theta? And do you agree that x in general is the same as r cosine of theta? So if I whack this down here, if x equals r cosine theta in general and y equals r sine of theta in general, then what must I do to substitute these in up here? Well, I'm going to have x squared, which is r squared cosine squared theta, plus y squared, which is going to be r squared sine squared of theta, equals to 25. I notice that there is a common factor of r squared, so this is r squared lots of sine squared theta plus, let's get it the right way around. This is r lots of cosine squared theta plus sine squared theta. And then, pretty obviously, cosine squared plus sine squared, we should know from our trigonometric work earlier on, this just equals to 1. So actually, in polar coordinates forms, r squared equals to 25, and since r has to be a positive quantity, that just means r equals to 5. So now this is actually a really easy question, because now all I have to do is to find the area of r. I just have to integrate a half, I can take that half out as a factor, r squared, well I know what that is, that's 25, d theta, and now I just have to integrate between the two bounds. Well, what is that? That's going to be inverse, so this is theta 1, and theta 1 is clearly the inverse tan of opposite, which is 3 over adjacent, which is 4. And theta 2 is clearly inverse tan of opposite, which is 4, over adjacent, which is 3. So that means I have to integrate between inverse tan of 4/3 as the bottom limit. What's going on here? No, come on. 4/3 and inverse tan of 3/4. That's it. That's all I need to work out. So actually this is going to be pretty easy to do. So r is just going to be 25 over 2, and then this, I mean, if you want to see it another way, since theta is a dummy variable, this is the same as a half of the integral of 25 dx between inverse tan of 4/3 and inverse tan of 3/4, right? Because you can make the substitution, let x equal to theta, so that dx equals d theta, and then you're away. But you know, this is by the by, so then this will integrate to x, so then this will just become the inverse of tan of 4/3 minus the inverse tan of 3/4. And now if you want an exact value of this, I mean, you could just plug this into a calculator and figure it out to so many decimal places, but if you want the exact value of this, the way to deal with tans and tans, or inverse tans minus and inverse tans minus, is remember that tan of a minus b equals tan of a minus tan of b all over 1 plus tan a times tan b. So what I'm going to do is I'm going to take the tangent of the inverse tan of 4/3 minus the inverse tangent of 3/4. And then once I figure out what that is, I'll just inverse tan both sides. So tan of this thing is clearly just 4/3 because tan of inverse tangent cancels, minus tan of this thing, which is 3/4, all over 1 plus 4/3 times 3/4, I believe is just 1, isn't it? So this all becomes over 2. 4/3, if I get it into twelfths, that's 16/12. And if I get this into twelfths, that's minus 9/12. 16 minus 9, I believe, is 7. So it's 7/12, so it's 7 over 24. So actually, this stuff here is actually the inverse tangent of 7 over 24. So if you really want to be specific, r is 25 over 2 lots of the inverse tan of 7 over 24, and that's the exact value of that area. Okay, so there's lots of ways you could have done this question, but that's how you would have solved it using polar coordinates. So the main takeaway here is that when we're integrating, we're dealing with infinitely skinny sectors of angle d theta, and we're using the limit that d theta tends to 0. What we need to do is integrate r squared d theta between the two limits. And if you have to rearrange r a little bit so it's a function of theta, because essentially what you're doing is you're integrating r as a function of theta. Okay, so you need to make r a function of theta. In this case, r was just 5. That's a really easy function of theta. And generally speaking, whenever you've got a problem that's what's called radially symmetric, 2 m's there, radially symmetric. Whenever you've got a problem that's got some kind of rotational symmetry, or we say that's radially symmetric, it's generally a lot easier to solve it using polar coordinates, as demonstrated here. You know, instead of doing lots of integrals and taking away funny sectors and all this business, all I had to do was integrate 25 over 2 between two inverse tangents, and the inverse tangents were pretty easy to deal with so long as I knew my trigonometric identities, and I could have just plugged it in. Okay, before we move on to some questions, there are a couple of little problem solving things. Okay, and they're to do with sketching. Okay, so sketching. Okay, you won't necessarily get tested on this, and to be honest, most Casio CG50s and whatever, you can actually use the sketch function. It's not that difficult to use. You know what? Explore with it, figure out how you do it. I could go through with it, but to be honest, part of the fun is knowing how to sketch these things without a calculator. So I'm going to talk through some of the techniques. Okay, suppose I've got the function r equals, and then let's say I've got 2 plus 2 cosine 2 theta. Okay, here clearly r is a function of theta. Then the question is, what does that look like? Well, the first easy technique we can think of is we can say, okay, from the initial line, are there any values of theta for which this function does not exist? Doesn't seem that way because cosine is defined for all values of theta. So that's okay. Next up, I'm going to say, okay, well, let's plug in some initial values, or some values to at least see what's going on. So here, clearly, when we're on the initial line, theta is 0. When we're pointing vertically upwards, theta is pi over 2. When we're pointing to the left of the initial line, this is when theta is pi radians, and we're pointing downwards, this is when theta is 3 pi over 2, and then when we go back to the initial line, this is 2 pi, and so on as we wind round. Next up, I want to notice the arguments. This is 2 theta. So any value of theta I plug in is going to get doubled. So maybe it would be an idea to halve all of these initial right angle things that I put down, purely because I know when I double it they become right angles and I know how to deal with that. So I also want to imagine what happens over here when theta is pi over 4. I want to know what happens over here when theta equals 3 pi over 4. I want to know what happens down here when theta is 5 pi over 4, and down here when it's 7 pi over 4. Okay, now if you really want to, and it's a bit babyish, if you're unsure what's going on, you can create a table, right? And with skill and practice, you can probably figure out what's going on. You can say, well, okay, so let's say we've got our theta value and we've got zeros, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Let's one complete spin. What is R? Okay, so let's draw a cosine graph just to familiarise ourselves what's going on here. So cosine is going to look like this, between 0 and 2 pi, where it oscillates between 1 and minus 1. So when I plug in theta is 0, cosine of 0 is 2, so I've got 2 plus 2, so the R value is 4. That's good, so immediately I can put a little cross there at 4, so that's fine. Next up, when theta is pi over 4, then 2 theta is pi over 2, and pi over 2 in terms of cosine, well, cosine of pi over 2 is just 0, so it becomes 2 plus 2 lots of 0, so that's 2. So immediately the radius has shrunk by 2 here, so we've got some kind of function doing something like this maybe. And then when we're at pi over 2, then 2 lots of pi over 2 is pi. So cosine of pi is minus 1. 2 lots of minus 1 is minus 2. So then if I have 2 plus minus 2, that's a 0. So we're popping into the 0 like that. Okay, so that's a 0. 3 pi over 4. Well, have I missed something? No, fine. 2 lots of 3 pi over 4 is 3 pi over 2, and 3 pi over 2 is here, remember. So that's 0, so then that becomes a 2. So it's going to be out here again, that's 2. That's interesting, so it's doing something like this maybe. So that's a 2, and then when it's pi, well, that's going to be 4, because cosine of 2 pi is 1, and 2 plus 2 is 4, so it's going to be back out here at 4 again. Okay, 5 pi over 4. Well, if I continue the cosine graph looking like this, then this maximum height here is at 4 pi. This point here is half a pi on from 2 pi, so it's 4 halves, so that's going to be 5 pi halves. This is going to be 3 pi, and this is 7 pi halves. So 5 pi over 4 doubled, because we're doubling the thing, is going to be a 0 when I plug it into cosine, so that becomes a 2 again. So it's going to be back here at 2. 3 pi over 2, when I double it, is going to be 3 pi, so it's going to be minus 1. So 2 plus 2 lots of minus 1 is a 0 again, so it's going to pop in like this. And then 7 pi over 4, if I double it, is 7 pi over 2, and that's a 0 on my cosine theta, so cosine of that is 0. 2 plus 2 lots of 0, that's going to be popping out to 2 again. It's going to look like that. And then you can probably tell that it's just going to do something like that. So in actual fact, r of 2 plus 2 cosine of 2 theta appears to be two circular-like objects. They may not be circles, maybe it's an infinity loop, you know, lots of different things. And if you're really interested, what you can do is, I recommend you go to something, there's lots of websites. One of them is wolframalpha.com, and another good one is desmos.com. So if I go to wolframalpha.com, I'm just doing this now, and I type in plot, and then you want to type the thing you just had, so r equals 2 plus 2 cosine 2 theta. And really, to enter in a theta, you can just put theta and put a star and 2. So let me just check that works. Plot r equals 2 plus 2 cosine of 2 star theta, where star is shift 8 on most keyboards. Then yeah, you should have a nice diagram where it says polar plot. Yeah, so that should be hopefully convincing enough. And what have I done here? There should be a 0, 2 and a 4. Cool. Now, a little word of warning about that. Some graphs have what's called dimples. So for example, let's suppose you did that plot and you can't tell if your plot does this, in which case there's two little dimples here, or whether your plot does something like this and it's circular. Because say for example you've been incredibly lazy and you've only checked theta is 0, theta is pi over 2, pi over 4, sorry, theta is pi over 2, and say you've not gone sufficiently small enough angles of theta and you're worried that you've missed something along the way. Well, we can actually use calculus to determine what's going on here. So, put it this way. When we're back here, do you agree that if I was to draw a vertical line, that there should be 2 points that just touch that vertical line, if there was a dimple? And if I was to draw a vertical line back here, there should only be 1 point in which it touches. Now, what is the equation of that vertical line? Well, think about what we're doing. We're minimizing, if you think about it, the x-coordinate given for a theta value. So we're setting dx by d theta and setting it equal to 0. Okay, so that's one bit of calculus we can use. And by the way, x equals r cosine of theta. So r would just be your function of theta. So all you have to do is times your r function of theta, times it by cosine, and then dx by d0. So in this thing up here, and by the way, by doing that, technically you're also finding the maximum and setting it equal to 0. So really for this question, we should have 1, 2, 3. If I look up here, if I try it in my previous example, how can I check there's no dimples horizontally? Well, then I need to show that dx d theta equals to 0 only has 1, 2 solutions, right? So x, remember x is r cosine theta, because I've explained why up here just by looking at a right angled triangle, just from what the coordinate system's about. Then I've got r times by cosine theta. So that means x is going to be r, so that's 2 plus 2 cosine 2 theta times by cosine theta. So now x is actually 2 cosine theta plus 2 cosine theta times by cosine of 2 theta. And now I want to differentiate that with respect to theta and set it equals to 0. So first things first, 2 cosine theta just becomes minus 2 sine theta. That's easy. The next part is going to be 2 lots of, and we're going to need to differentiate this thing. So leave the cosine theta alone first and differentiate the cos 2 theta. Actually, the other way around. We'll differentiate the cos theta. We're going to have to use the product rule. So cosine theta becomes minus sine theta and then times by the cosine 2 theta. And then we're going to have to add. And then we've got cosine theta, but now we have to differentiate cos of 2 theta. So cosine differentiates to minus sine, so this will actually be minus sine of 2 theta. But then remember the argument has to come out and differentiate it, so 2 theta differentiates to 2. So now, in actual fact, we've got it. So this looks particularly nasty, but we can actually spot that everything has a factor of 2. So if I divide by 2, that goes and that goes. So we've actually got minus sine theta cosine 2 theta minus 2 lots of cosine theta sine of 2 theta equals to 0. Okay, first thing I'm going to do is I'm going to expand this sine of 2 theta term right here. Because remember, sine of 2 theta is 2 sine theta cosine theta. And if you're unsure about these trig things, you need to go back and memorize them. There's literally no point, because you're going to understand this stuff so far, and you're just going to fall at a hurdle because you don't know your trig. So you're going to have minus sine theta lots of cosine 2 theta, and then you can have minus 2 times this 2, which is 4, lots of sine theta, but then you're going to have a cosine theta times by this cosine theta, so that cos and that cos will make a cos squared of theta, which is this. Now, you can times everything by minus 1, so essentially that disappears, that becomes a plus, that becomes a plus, that's fine. And then notice that every single factor now has got sine theta involved, so we can factorize. We can say that sine theta, and then we've got 1 plus cosine 2 theta, and then we've got plus 4 cosine squared theta, like so. Cool. Equals to 0. So we're either going to have solutions where sine theta equals to 0, and if you think about what that implies, that means theta either equals to 0 or pi, or 2 pi, or just in general some multiple of pi. What does that equate to on our diagram? Well, when theta is 0, we're here, aren't we? Remember, theta's 0, and when theta's pi, we're over here. And when theta's 2 pi, we're back over here. And when theta's n pi, we're over here. And so on and so on. And it keeps bouncing between the two left and right points. So indeed, actually, that sine theta equals to 0 has solved it. But we still have to consider this thing. And so cosine 2 theta, if I make this in terms of 2 cosine squared theta minus 1, notice how this whole thing can become a quadratic and cosine squared. So this becomes sine theta of 1 plus 2 cosine squared theta minus 1 plus 4 cosine squared theta equals 0. The 1s and 1s cancel. I've got 2 cosine squared plus 6 cosine squared, which is 6 cosine squared theta. So now I'm dealt with the case where cosine squared theta equals to 0. So cosine theta equals to 0. And when does cosine theta equals to 0? This equals 0 when theta is an odd multiple of pi over 2, doesn't it? I.e. pi over 2, 3 pi over 2, and so on. Okay, what does that correspond to on our graph? Well, when theta is pi over 2, we're at 0. When theta is 3 pi over 2, we're at 0. So in actual fact, it's found this one as well. But luckily for us, we're not particularly interested in that, because although technically is a minimum in a restricted domain, for example, if I was only interested in this side of the graph, then yeah, technically it's a minimum of that left-hand side. So what it's essentially saying is there's no weird overlappy dimples going on in the middle. So actually that's perfectly fine. Yeah. So the endpoints, or rather the points where we've got minimums and maximums or possibly overlaps, is just going to be coming from dx d theta. And in a similar way, if I had vertical maximums or minimums like so, then I would just do dy by d theta equals to 0, and I would solve in a similar way. I would have some quadratic equation to solve, not quadratic, I'd have some trigonometric equation to solve, and I'd just be really, really careful. Okay, and the same reason I would let y equals r sine of theta. Okay, and why is that? Because we talked about this earlier up here. Yeah, y is r sine theta, x is r cos theta. Cool. Right, well that's pretty much all you need to know for polar coordinates. Being able to sketch them, be able to find areas, to find equation of tangents. Well, there's nothing real new here. I mean, if I've got dy by dx and I want to find the equation of any point on that line, so if I want to find the gradient, okay, if I want to find the gradient on a, in terms of polar coordinates, well, this isn't anything new. This is just going to be dy d theta divided by dx by d theta. Okay, this is just parametric differentiation. You guys should be totally okay with that. Yeah, that's pretty much it. To find the second derivative, I remember doing this. So if I want to find the second derivative of y with respect to x, remember you can only differentiate with respect to theta because r is a function of theta, and you're living in an environment essentially that only deals with functions of theta. So let's think what we need to do here. So if I differentiate, if I take dy by dx and I differentiate that with respect to theta, then that will get the d2y on the top, but I'll have a d theta dx on the bottom, and technically I want a dx squared on the bottom. So I would have to times that by d theta on the top and d theta dx on the bottom. So that's essentially dividing by dx by d theta, like so. So in general, if you want the nth derivative, then you have to do the n minus 1th derivative, there, like so. So if I want the third derivative, I need to do d by d theta of the second derivative over dx d theta, and so on. And this is just a consequence of the chain rule. Maybe when you understand that and you can figure that out, then you really have this chapter nailed. But yeah, that's pretty much it in terms of theory. I think I need to just go over a couple of questions to nail it in. So here you go. Pause the video, give it a go yourself. I'm just going to grab a drink, but give it a go. Okay, so figure 1 shows the curve by the polar equations blah and blah. Well, clearly r equals 2 is labelled as this thing. It's this quarter circle. And r equals 1.5 plus sine of 3 theta is this weird petal shape type thing that probably goes off in different directions, but we'll leave it as that. Find the coordinates of the points where the curves intersect. Well, just as you expect, you'd set them equal to each other. So set 2 equal to 1.5 plus sine of 3 theta. For minus 1.5 both sides, that's half equals sine of 3 theta. And remember that from my sine graph, like so, that if that's 1 and that's minus 1, then a half is dead in the middle, and that's got a principal value there. Well, if that's pi, this is a third of pi, and if I go along by symmetry, this is 2/3 of pi. So if I was to split this up, that means either 3 theta equals the inverse sine of a half, which is pi thirds, plus multiples of 2 pi, or 3 theta equals the other one, which is 2 pi thirds, plus integer multiples of 2 pi. Well, if I divide by 3 both sides, I'll get theta equals pi over 9 plus 2n over 3 lots of pi, or theta equals 2 pi ninths plus 2n pi over 3. Now, because this function is between 0 and pi over 2 in terms of radians, then adding or subtracting 2/3 of pi isn't going to give us any more solutions within that range. So clearly the theta values are pi over 9 and 2 pi over 9. So when it says find the coordinates of the points where the curves intersect, then clearly the theta values are pi over 9 and 2 pi over 9. And remember, I want the r values, but clearly because they lie on the curve r equals 2, I know that I can just put a 2 in there. So in actual fact, these are my answers for part A. So that wasn't too bad. Okay, the region S between the curves, for which r is 2, and for which r is greater than 2, but for r is less than that, is shown. Find by integration the area of the shaded region S given your answer in the form blah blah blah. Okay, so if we're going to be doing, let's think about this very carefully. If I'm going to be doing integration by this time polar coordinates, which is going to be dealing with sectors, then if I draw a line up from here to here, and this is theta is 2 pi ninths, and I draw a line from here to here, and this is when theta equals pi over 9, then if I was to integrate the outside one, which is this, and technically it's squared, you know, between those two, I would get technically this whole thing. But really, I'm going to have to minus the area from R2. Right? Do you see how, if I, let me draw a sketch. Right, so if I was to do the integral between 2 pi ninths and pi ninths of r squared, which is 1.5 plus sine of 3 theta squared d theta, that would give me on my sketch, if I want to do this roughly right, that's my r is 2, then I've got this weird tulip thing looking like that, then that would give me this whole area. Whereas if I did the integral of between 2 pi ninths and pi ninths of the other thing squared, which is the other r, 2 squared d theta, then that would give me, well, there's r equals 2, there's my other tulipy thing looking like that, then that would just give me, oh no, it's not all of this, is it, you silly boy? It would be from there to there. It would be, I need a finer highlighter, it would be this sectory bit like that. It would be this. So do you agree? Oh, let's not use green. Let's use orange. Right? So the way I like to think of it is the integral on the left is the whole pizza, and the integral on the right is the bit without the crusts. And really what we're trying to do is we're trying to find the pizza crust. So clearly, as far as I'm concerned, we need to do this integral on the left minus the integral on the right. And because they have the same limits, we can just subtract one from the other. So the region we're interested in, S, is just going to be the integral between 2 pi ninths and pi ninths of 1.5 plus sine 3 theta squared minus 2 squared d theta. And that's just something we're going to have to deal with. Okay, fine. So let's deal with this integral then. 2 pi ninths and pi ninths. Okay, let's just expand. So 1.5 is 3 over 2. When I square that, that's going to be 9 over 4. Plus 1.5 times this, but there's 2 lots of them, is going to be 3 lots of sine 3 theta. And then plus sine squared of 3 theta. And then I'm obviously going to minus 2 squared, which is minus 4. Now minus 4, okay, no, we'll leave that, Okay, we can tidy this up. 4 is technically 16 quarters. So 9 quarters minus 16 quarters, I believe, is actually minus 7 quarters. Okay, we've now got to integrate this thing. So that's pretty easy. We integrate between 2 pi ninths of pi over 9 of minus 7 quarters d theta plus the integral 2 pi ninths of 3 sine 3 theta d theta plus the final integral between 2 pi ninths and pi ninths of sine squared 3 theta d theta. Okay, now just to clarify, this integral is easy, this integral is easy, this one we have to do a little bit of a trigonometric rearrangement. And I've said before, whenever you integrate sine squared theta, or sine squared x, or cosine squared x, you've always got to consider cosine of the double angle. So here, if the angle is 3 theta, I need to consider cosine of 6 theta. Well, cosine of double that angle is just going to be 1 minus 2 lots of sine squared of 3 theta. Okay, and if you can't see where that came from, you do need to go back and do the trigonometric chapter again, because I'm going to start to assume that it's just common knowledge at this point. I make sine theta the subject, so I add that over and divide by 2, so I've actually got a half minus a half cosine 6 theta, and this is going to be sine squared of 3 theta. So in actual fact, I'm hoping you can see, that's a terrible d theta, I can just get rid of this, and I can bring this stuff down, whack it here. I can actually tidy up some more, because I can take this half out, and I can add a half to this, which is 2 quarters, so this actually becomes minus 5 quarters. Okay. Now, you could actually cheat like an absolute sucker and plug this into your calculator and do it. I'm going to show you how you do it without it. So let's just deal with this. So the integral now becomes, and it might need a new page. Maybe I'm writing too big, I don't know. Right, so what will this integral be? Well, this integral, I can combine them again. I don't know why I separated them. I just wanted to show you that you could. Anyway, so minus 5 quarters will become minus 5 quarters of theta. Sine of 3 theta, well, sine integrates to minus cosine, so it's definitely going to be a minus, but then I have to divide by the argument differentiated, take that into account. So I believe that's cosine of 3 theta. And if I differentiate minus cos 3 theta, does that go back to this? And yes, it does, because 3 theta differentiates to 3, so a 3 would come out, which is good. And minus cosine becomes a sine, so that is good as well. So that's okay. That's integrated successfully. Next up, minus a half cosine 6 theta. Well, cosine integrates to minus sine. No. Cosine integrates to sine. But there's a minus there, so it'll be a minus a sine of 6 theta. But then I'm going to have to divide by this thing differentiated, the argument differentiated, so that's 6. So I believe that's going to be a minus a 12th. If I check this, sine differentiates to cos, which is good. The minus stays the same. The 6 differentiates to a 6. 6 theta differentiates to 6. 6 times a half is 6 times a 12th is minus a half. Good, that's fine. So now all I need to do is evaluate this between 2 pi ninths and 1 pi ninth. So, let's deal with this bit first. Now you could do the whole brackets, brackets, minus brackets, brackets, and this is 2 pi ninths, and this is pi ninths. But what I'm probably going to do is, for the first term, it's just minus 5 quarters of 2 pi ninths minus a pi ninth, which is just a pi ninth. So that's that first term done. Minus, and then I've got cosine of 2 pi ninths times 3, which is 2 pi thirds, minus cosine of pi ninths times 3, which is a third of pi. And then I've got minus 1/12 of, well, what's 6 times 2 pi ninths? Well, that's 12 over 9. You can divide that by 3. That's 4 thirds, isn't it? So sine of 4 pi thirds minus, and then it's going to be half of that, which is sine of 2 pi thirds. Cool. So this is the thing we need to evaluate. So minus 5 quarters times pi ninths. Well, I believe that's minus 5 pi over 4 times 9, which is 36. So that thing's done. Minus, and now let's use a different coloured pencil. So what is cosine of 2 pi thirds? Well, okay, let's draw my cosine graph. Right. This is half of pi. And if I go back a sixth of pi, this is a third of pi. And I believe that's a half. Cosine of pi over 3 is a half. So if I go forward a sixth of pi, I would actually get minus a half, and that's 2/3 of pi. So this thing is actually minus a half, and this thing is actually positive a half. So I've got minus a half minus another half, so this whole thing becomes minus 1, but I've got a minus in front, so I'll leave that as a minus 1 for now. And I've got minus a 12th of, let's check out sine. Sine does this. And what I'm interested in, 4 pi thirds and 2 pi thirds. Interesting. Well, there's pi. Well, a third of pi is root 3 over 2. And 2/3 of pi by symmetry is the same thing. So this thing is actually root 3 over 2. But then 4 pi thirds is another third pi onwards. So by symmetry, that would be minus root 3 over 2. So I've got minus root 3 over 2 minus another root 3 over 2, which is a whole negative root 3. So this whole thing becomes negative root 3. So I've actually got that. Right. Minus minus 1 becomes plus 1. Minus a 12th times minus root 3 is actually plus root 3 over 12. And this is minus 5 pi over 36. So actually we're done. But what does the question want? Given your answer in the form of a pi plus b root 3. Right. What's been the hubbub here? Have I made a mistake? I feel like the number term should have cancelled then. There shouldn't be a minus 1. That's interesting. What have I made a mistake on? Find by integration the area of the shaded region S. Yeah, no, I've done all this. And then, so, okay, so it's r squared, yes. 1.5 is 3 over 2. Let's get my calculator out. So 1.5 times 1.5, whoops, 1.5, it's definitely 9 over 4. But if I minus 4, it's going to be minus 7 quarters. No, that's fine. And then I've got double 1.5 times that, which is yes. Yeah, no, that's fine. So this is legit fine so far. Cosine of a double angle is 1 minus 2 sine squared. No, that's fine. Add that over divided by 2. This is fine. So I'm going to have a half. So if I add 0.5 to that, yeah, this is definitely right. Okay, so this line's perfectly fine. Was it here I made a boo-boo? Sine of 3 theta integrates to this, does it? Cosine differentiates to minus sine, but there's a minus there, so that's fine. Just double check. Sine differentiates to cosine, differentiates to minus sine, differentiates to minus cos, back around. So sine will integrate to minus cos, yeah, that's fine, and divide by the argument, yeah, no, that's fine. Then cosine, negative cosine will integrate to a minus sine, yeah, that's fine. Okay. Let's get my angles in radians. So what am I saying? I'm saying, really? Cosine of 2 shift pi over 3. That's definitely minus half. And if I do that with just pi, it's positive a half. Yeah, so that's minus 1. That's weird. I've definitely done the right integral. Yeah, I've done the outside one. Yeah, minus the inside one. Ah, well, technically, I've forgotten the half on the outside. There should be a half, right? Because, yeah, okay, fine. It should be a half. That 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 should be a half of all this. This should be a half of all this. And it should be a half of all this. But that's fine. Where's this plus 1 coming from? Let me try integrating. What is it I'm wanting to do? 1.5 plus sine of 3x. Let's make that squared. Minus 4 between 2 pi over 9 and pi over 9. Whoops, not pi 0.9. No. Oh, that's juicy. Right, the indefinite integral should have been minus 5/4 theta. Yeah, we've got that. Minus a 12th of sine 6 theta minus cos 3 theta. Yeah, no, I've done that 100% right. That's weird. Given your answer in the form of a pi plus b root 3. No, I've done this right. That's so bizarre. Where's this extra 1 coming from? Given your answer in the form of a lots of pi, where a and b are simplified fractions. Well, okay, fine. Yeah, if you want to be weird like that. Okay, so half of all this. So we've actually got minus 5 pi over 72 plus a half plus root 3 over 24. Common denominator, these two things, I guess half of 72 is 36. So this is actually 36 minus 5 pi over 72 plus root 3 over 24. And if I want to take a factor of pi out of here, then I guess I could just put a pi there and a pi here. and then the fraction of root 3 is just going to be 1 over 24. So this would be my A and this would be my B. Multiple of pi and multiple of 1 over 24 as a simplified fraction. Yeah, that's weird. I've definitely integrated it right. This is definitely the correct integral. I think I've substituted all the values in correctly. That's weird. Maybe there's a typo in the question. No, I've definitely done it right. Weird. Well, I'll do another one. Hopefully that will be clearer. I hope you guys didn't struggle too much at that. Anyway, let's crack on. So pause the video if you want. Let's go through this question. So the curve C shown in figure 1 has polar equation 2 plus cosine theta. At the point where A is on C, the value of R is 5/2. Okay, so I know that the distance from there to there is 5/2. So if I was to work out the theta value for that, then I would substitute 5/2 into there to get 5/2 equals 2 plus cosine theta, minus 2 from both sides. 2 is 4/2, so this is 1/2 equals cosine theta. Inverse cosine both sides. Inverse cosine of a half, let's just not mess around, is 1/3 of pi. And there's other solutions as well, but seeing as I'm only interested in theta between 0 and pi over 2, I can stop there, that's perfectly fine. So A has coordinates 5 over 2, comma, pi thirds. Okay. The finite region R, the point N lies on the initial line AN and is perpendicular to the initial line. Fine. The finite region R shown in the shaded figure 1 is bounded by curve C and the initial line. Find the exact region. Okay. Well, clearly, if I integrate between pi over 3 and 0 of 2 plus cosine theta all squared and halve it, d theta, then what I will get is that is terrible, I will get, I hope you can see, this massive region here. So clearly, once I've found that region, I'm going to need to take away that white triangle, and then I'm done. Okay, so technically, I then need to minus the white triangle. And what do I know about this white triangle? Well, that it's a right-angled triangle with hypotenuse of 5 pi, oh, not 5 pi over 2, of 5 over 2. And this angle here is pi over 3, and that's 60 degrees. So the height y is just going to be 5 over 2 sine of pi over 3. So 5 over 2 times sine of pi over 3. So that means the height, that is actually 5 root 3 over 4. We could have done Pythagoras on this, it doesn't particularly matter. 5 over 2 to get the last height, I mean, well, we'd need, mate, come on. Um, 5 over 2 cosine of pi over 3 to get the horizontal, and that's 5/4. So really we need to do a half of 5/4 base times by height, 5 root 3 over 4. So this is actually going to be 25 root 3 over 4 times 4, which is 16, times 2 is 32. So now we just have to evaluate this integral between pi over 3, 0 of 2 plus cosine theta squared d theta. Same thing again, so let's integrate pi over 3, 0 of half of, and let's square this thing, so it's 4 plus 4 cosine theta plus cosine squared theta, d theta. Cosine squared, remember, or cosine 2 theta is 2 cosine squared minus 1. So that means a half of cosine 2 theta plus a half equals cosine squared theta. So this is actually going to be the integral between pi over 3, 0 of a half of 4 plus 4 cos theta plus a half of cos 2 theta, d theta. Let's tidy up. 4 plus a half, well, that's going to be 9/2 plus 4 cos theta plus a half cosine 2 theta. Let's integrate this now. So it's going to be a half of 9 over 2 integrated is 9 over 2 theta. 4 cos theta becomes 4 sine theta. And a half cos 2 theta becomes a quarter of sine 2 theta, I believe. And this is between pi over 3 and 0. So this is going to be a half of sub in pi over 3 minus, and then when I sub in theta is 0, because this is a theta, this is sine theta, and sine of 2 theta, this is just going to be a 0 as well, so that's relatively easy. So 9 halves of pi thirds, well 9 divided by 3 is 3, so this is going to be 3 halves of pi. Sine of pi over 3 is root 3 over 2, I believe. Sine of, just checking, don't want to be making mistakes at this stage. Root 3 over 2, so when I times that by 4, that's going to be plus 2 root 3. And then I've got a quarter of sine of double that, which is 2 pi over 3. Which is also root 3 over 2, so I've got a quarter of that, that's going to be plus root 3 over 2 with a quarter, that's an eighth. So this is going to be a half of 3 halves of pi, and then 2 is 16 eighths, but plus another eighth is going to be plus 17 root 3 over 8. And then when I halve that, that's going to be a half of 3 halves, which is 3 quarters of pi, plus a half times that is 17 root 3 over 16. So if I back it up, we've now, so coming on from here, we've actually got 3 quarters of pi plus 17 root 3 over 16 minus 25 root 3 over 32. Remember, we had to take away the triangle. 16 72ths, 32nds, if you want to call it that. At least I have a common denominator. I can times this by 2, top and bottom. 17 times 2 is 34, that's 32. So this is actually 3 quarters of pi. And then 34 minus 25 is 9, isn't it? So this becomes plus 9 root 3 over 32. And 32 is 2 to the 5. 9 is 3 squared, so that's not going to cancel. So that would be my exact answer for that one. Yeah, nice. Okay, yep, pretty straightforward. Maybe there's a typo, it just seems a bit weird in the previous one. It's the same method, just finding areas. Okay, now this question was on the last year's A-level further maths paper. So give it a go. You may have to use some derivative tricks. And yeah, pause the video, give it a go. Okay, figure 1 shows the design for a tabletop in the shape of the rectangle ABCD. The length of the table is 1.2, the area of the closed curve is made of glass, and the surrounding area shown in figure 1 is made of wood. The perimeter of the glass is modelled by the curve with the polar equation blah, where A is a constant. Show that A is 0.2. Okay, I am going to assume, even though it's not said in the question, that these points here and here, the glass and the wood just touch. Okay, so what I want really is I want to find a maximum dr by d theta and set that equal to 0. So differentiating r with respect to theta, 0.4 disappears, so dr by d theta, that's going to be a 0 to begin with. Then a cosine 2 theta. Well, cosine differentiates to a minus sine, so this will actually become minus 2a sine of 2 theta. Now if I want this to equal 0, minus 2a, oops daisy, sine of 2 theta equals to 0. Since minus 2 and a are constants, I'm going to ignore them. So when does sine of 2 theta equals to 0? Well, sine of theta oscillates like this. You know, it's the sine graph, but twice because of the contraction. So that's going to be pi, and that's going to be 2 pi. So actually, theta is going to be pi over 2, pi, 3 pi over 2, and 2 pi for when it's a minimum or maximum. And those are the only ones between 0 and 2 pi we're allowed anyway, in that region. So let's see what happens when I plug in pi over 2 into these things. Well, what is cosine of 2 lots of pi over 2, which is pi? Well, here's cosine. Cosine is going to look like this. So here's pi, here's 2 pi. Now, if I was to keep going, because I'm doubling this thing, then this would be 3 pi and this would be 4 pi. So clearly, when I put cosine of pi or cosine of 3 pi in, they're going to give negative values. So I've got minus 0.4 minus a as my radius. And when I substitute in pi and 2 pi, that's going to be cosine of 4 pi and cosine of 2 pi, which is 1. And technically I can have theta as 0 as well into this because we're allowed it, but whatever, it's going to be the same deal. So it's going to be 0.4 plus a. So I'm taking a to be a positive constant. Well, it doesn't particularly matter here. If a was negative, then this would be the maximum. So if I take this to be the maximum and this to be the minimum, say, and the only reason I'm taking it to be the maximum at the top is because I'm going to imagine, to me it makes the most sense, if right in the middle of this table, my initial line is pointing this way. It's not actually said in the question, by the way. I think Edexcel have done a pretty poor job of writing this question. But let's suppose that at this point, this is when theta is 0. At this point here, this is when theta equals pi over 2. And at this point, pointing back here, this is when theta equals to pi, and so on and so on. And clearly, when theta equals to 0, we're pointing all the way to the right. So we're in the middle of the table, and we're half of 1.2. So this whole thing should be 0.6. And clearly 0.4 plus what is 0.6? This must mean that a equals 0.2. There's so many assumptions to this question. I don't think it's particularly well laid out. It could have said that the glass is tangent to the bit of wood, or the wood just covers it at the edges to the far right. Whatever. Oh, hey, okay. Hence, given that AD is 60 centimeters, so from here to here is 0.6 meters. I don't know why they've given it. Why? Why would you? Yeah, this is just poor for me, because they've given it in meters. And then they've deliberately gone for centimetres when they could have just said 0.6 metres. It's like they're wanting people to mess up. It's just not nice. Find the area of the wooden part of the tabletop given your answer in metres squared. Well, if it's not obvious, we need to do the area of the rectangle, which is 0.6 times 1.2, which is 0.72 metres squared. And then we need to minus the integral of the region between whatever and whatever. So, interesting. There's a lot of radially symmetric things going on here. For example, to make things a little bit easier, I knew that this is clearly the minimum, right? So this point here where the first minimum is, that must be when theta is pi over 2. So do you agree, by symmetry, that if I find the area of this region here, all I have to do is times it by 4, because I can split this up into 1, 2, 3, 4 sections. So really, all I have to do is 4 lots of this integral, which is going to be between 0 and pi over 2, of r, which is 0.4 plus 0.2 cosine 2 theta squared d theta. It's not much of a problem. So this becomes 0.72 minus 4 times a half, so that's 2, integral 0 pi over 2. Now 0.4 squared, I know it's 4/10, I'm just very lazy, is 0.16, so that's 4/25. 4 times 0.2, 0.4 times 0.2, and then double it, means that we now have plus 4/25 of cosine 2 theta. Just double check, yep, cosine 2 theta, and then plus, and then we've got that 0.2 times 0.2 going on, which is 1/25 of cosine squared of 2 theta d theta. Done, done. Okay, I can take the factor of 25th out for no particular reason. So this is 2/25. This is 0.72 integral pi over 2 theta, and then this is going to be 4 plus 4 cosine 2 theta plus cosine squared 2 theta d theta. Same deal again to integrate. The rest of them are quite easy to do. So this is going to be 0.72 minus 2 over 25 of 4 becomes 4 theta. 4 cos 2 theta is going to become 2 sine 2 theta. Cos squared, same rule again. Cosine 2 theta equals 2 cos squared theta minus 1. So that means a half of cosine 2 theta plus a half equals cosine squared theta. So when I integrate a half, that becomes a half theta. So 4 thetas, which is 8 halves plus another half theta. This will actually become 9 halves of theta. Then half cos 2 theta is a quarter of sine 2 theta. Yeah. And this gets integrated between pi over 2 and 0. We can ignore the bottom limit of 0 because when I plug 0 into this thing, well, sine of 0 is 0 and 9 halves of 0 is still 0. So this becomes 0.72 minus 2/25 of 9 over 2 times pi over 2, which is 9 pi over 4, plus 2 lots of sine of pi, is 0. Wow, really? That's cool. Sine of pi is 0, so actually these terms disappear entirely. That's cool. So we've got this. So the answer is actually 0.72 minus 2, well the 2 and the 4 can cancel, so I've actually got 9 pi over 50. And I believe the question wanted it to 3 significant figures, so 0.72 minus fraction 9 pi over 50. So to 3 significant figures, I make that 0.155 meters squared. Yeah, to 3SF. Cool. Well, I hope you enjoyed that. Polar coordinates are really useful, and they just use lots of skills from trig, integration, a little bit of substitution. There are going to be harder problems, but yeah. Okay, see you later.